Welcome. This video is going to finish looking at the topics covered in Section 1 of Chapter 5 in the Brown SL Chemistry book. So specifically, we're looking at enthalpy changes, and we're going to look a little bit here at the direction of change, or what's called the natural direction of change. So reactions have a natural direction toward lower potential energy, just like everything we do in nature. If you slip on a ladder, you're going to fall down, not up, because down takes lower potential energy or has lower potential energy than going up. You'd have to put energy in to fall up the steps. So same thing happens with reactions. They go toward lower potential energies. So this means exothermic reactions should be the natural direction for most reactions, since the products will have less potential energy or greater stability than the reactants do. So stability, though, it's a little bit tricky because it's a relative term. If you look at this graphic down here, H2O2 is a more stable product than H2 and O2, and we can see that in my graphic because here's H2 and O2. Oops, I don't have my marker. Way up here with H being the heat of reaction or the enthalpy. So much higher potential energy here for the elemental constituents. H2O2 quite a bit stabler, but it's far less stable than it is as water, which is why H2O2 breaks down fairly easy, especially in sunlight. So can't always just use the word stable. It has to be in comparison to something. This doesn't mean an endothermic reaction can't be the natural direction of a reaction. Certainly for some processes like ice melting, it's endothermic and it is the natural direction under standard conditions. So it's just unusual for an endothermic reaction to lead to lower potential energy. So when does it happen? Well, if you think of the natural direction moving toward greater disorder as well as greater stability, or instead of greater stability, those two things go hand in hand. Greater stability is actually greater disorder. Then endothermic reactions that involve the production of gas can be the natural direction of the reaction. The heat of combustion, or enthalpy change of combustion, is the heat produced when 1 mole of a substance is burned in excess oxygen. And heat of combustion is a common reaction in our day-to-day lives because we combust fuels to power a lot of equipment like our cars, and we also combust fuels to heat our homes and various things. More often we talk about the standard enthalpy of combustion, which is abbreviated as I've shown. It's got the subscript C to show it's combustion, or sometimes you write COMB to abbreviate combustion. But now we add the little standard superscript to it. And that just means it's the heat produced when 1 mole of a substance is burned under standard conditions in excess oxygen. It's often determined experimentally using a calorimeter, and we'll talk more about calorimeters, and it's calculated using MCAT, or the mass of the substance times the specific heat of the substance times the change in temperature. And I should actually have delta T there. So the enthalpy change of a reaction is commonly calculated by measuring the temperature change in water, and this can be done if the water is part of a calorimeter, either surrounding it or above a burning fuel, or if you're carrying out the reaction in an aqueous solution, like if you're doing a solvation or a neutralization reaction. So then the enthalpy change is usually expressed as kilojoules per mole when you're all done, with it being per mole of product that you're interested in. So 3 basic steps we follow to do these. We use water's mass and specific heat value to find the change in heat. We change the mass of the sample to moles, or fuel, and then we divide the change in heat by moles. And typically we'd have the heat in kilojoules, so we end up with our final answer in kilojoules per mole. So looking at this example here, if you had 0.45 grams of ethanol, and there's its formula, burned in a calorimeter, the calorimeter contains 200 milliliters of water, which increases in temperature from 22.5 degrees to 35.7. What is the standard enthalpy of combustion for ethanol? So I'm going to use MCAT. And my mass for water, 200 milliliters, because water has a density of 1 gram per milliliter, I can go ahead and sub in 200.00 grams of water. My specific heat value, I'm just going to go with 4.18. You could certainly have more sig figs if you wanted, but 3 is plenty because our temperature is going to limit our sig figs. And then for my temperature change, I have to take the 35.7 minus 22.5, which is going to give me a temperature change of 13.2 degrees Celsius. So I do hang on to 3 sig figs. And now I go ahead and punch these in. So I'm coming up with 11,035.2 joules. And I can hang on to all my sig figs till my final answer. So now I need to take my ethanol, my 0.45 grams, and I need to change this to moles. So I need to find the molar mass of ethanol. And I'm coming up with a molar mass of 46.08 grams per mole. So 0.45 divided by 46.08 is going to be about 100th, 0.0098, since I can hang on to 2 sig figs. And so this is my moles. So now if I go ahead and change my kilojoules, my joules to kilojoules, I actually have 11.035 kilojoules divided by the 0.0098 moles, which is going to give me a combustion of 1,126 kilojoules per mole, or if I remember my sig figs, I would round this to 1,130 kilojoules per mole. And remember, IB likes to write it mole minus 1, but when I see that, I just think per mole. And of course, this should be a negative value since it's an exothermic reaction. The water gained the energy, but the standard enthalpy of combustion is going to be exothermic or a negative value. Some other common enthalpies that you'll be calculating throughout the year are for neutralization reactions, for solvation or dissolving, vaporization or boiling, fusion, which is melting, and then heats of formation, which we'll talk about in a couple slides. Most of these values are going to be negative because they're exothermic reactions. The other thing you'll be asked to do, especially in experimental work, is to state all the assumptions we're making as we calculate these enthalpy changes. So some of the assumptions we're making is that all heat is transferred from the source to the water. In the case of solutions, we're assuming the specific heat and the density of the solution are equal to water. When we're burning fuels, we have assuming the fuel completely combusts, or if it's a solvation, we're assuming the solute completely dissolves. We're assuming that no heat loss goes on in the system, and we're assuming standard conditions are being used. And one assumption you can always make, regardless of how good your equipment is that the greatest source of air in a calorimeter is going to be heat loss to the surroundings. And so there is one small trick we can do experimentally to help minimize this loss in our data, or this discrepancy. So the idea is based on the fact that as soon as you mix something in a container, like when you're carrying out a reaction in a solution, as soon as the temperature of the solution begins to increase, there is going to be some heat loss to the surroundings because the surroundings are cooler. So you can minimize this heat loss using an insulated container and covering the container, but it still occurs. But we can also do something with our graph data to estimate this heat loss. Here's what I'm talking about. On this graph here, it looks like a mess, but along the bottom here, you've got your copper sulfate solution just sitting there at room temperature. We just took a few readings to verify the temperature is stabilized, it's not changing. And then right here at 100 seconds, some zinc gets dumped in, and it's actually an excess amount of zinc that's getting added to the copper sulfate. And then you see this increase in temperature. It goes up very quickly and then continues to increase till right here it reaches a maximum temperature of 61 degrees, and then the temperature starts falling off as the solution starts to cool. So that doesn't mean that the reaction is over. It simply means that the heat being produced is being lost at an equal rate. And the other thing we notice during this cooling is it's occurring at a very predictable rate here. So the slope is remaining very consistent. So what we can do is we can assume that this heat loss started right back here at the very beginning and that it was at this same rate. So that's why they extrapolate back, and we can look and see that the maximum temperature was actually probably more like 70 degrees because we know this heat loss started right away. So I'll just scroll up here a little bit, but basically that's what the rest of the slide explains, is why this extrapolation works to help give us an estimate of what would be a more reasonable or acceptable maximum temperature for our calorimeter.